Here are some problems that you guys are going to be working in chapter 5. And I want you all to be able to have a pattern to go on in order to be able to work similar problems such as this. So I'm not going to work these exact ones. I'm going to change a few things up here. So the problem that I'm going to work here with number 1, the question is electrons with kinetic energy of 1 MeV have a specific ionization in air of about 6,000 ion pairs per meter. What is the linear energy transfer of these electrons in air? So I'm not going to work the exact problem. I'm going to work something here that is fairly close to that, so that when you work the actual problem, you can see how this goes. Now, how does this work? If you've actually viewed or looked over the lecture for this particular chapter, you can see here that the linear energy transfer is going to be the product of two other things here. And I'm going to call one of them SI, which is the specific ionization. This is going to be the number of ion pairs produced per unit track length. So you can see here the units could be measured in ion pairs per meter, could be centimeter, depending on whatever the value happens to be. This is going to be multiplied by W, and W is going to represent the average energy for the formation of an ion pair in air. Now, it doesn't really matter what the energy is or the type of radiation. We just happen to know the constant here. The constant has been measured, and we're looking at the average energy being about 33.85 EV produced per ion pair in the air. So if you take the amount of EV per ion pair and you multiply it by the number of ion pairs per whatever the length is, in this case it happens to be meters, then you can produce the linear energy transfer at least per meter. So what this is going to end up being here, if you produce the two, which in this particular case, I chose 5,000 as opposed to 6, but the process is going to be the same. You end up with 169,250. So that's going to be 169,250. And that is basically going to be having that canceled out, and that's going to be EV per meter. Now, what are some of the ways that you can take this problem and make it harder? Let's say I don't want the answer in EV per meter. Let's say I want it in kilo electron volts per centimeter. Would I do something like that too? Sure, I would. So if I take 169 and 250 EV per meter, how can I change that into those units? Well, I have to do some conversions here. And what are those conversions? If I am looking to get my answer in KeV per cm, then I have to figure out how to change this into KeV, and I have to figure out how to change meters into centimeters. That part's probably not so hard. So 100 centimeters is equal to 1 meter. That's something you can look up in pretty much any table that you want to. And we also know that 1,000 EV is going to be equal to 1 KeV. Now I can take either one of these and I can write it with one divided by the other. And this is the same thing as saying 1. Because let's say I go through and I divide both sides here by 1,000 EV, then I get the same thing as I got over here, but that cancels with that, and that is equal to 1. Same thing happens up here. So if I want to change the amount of EV I have into KeV, obviously I got to get rid of the EV, and I've got to have the KeV in its place. So the only way I'm going to do that is if I have some sort of EV here in the denominator and a KeV in the numerator. So what I'm going to do is I'm going to take this particular conversion factor that I came up with, multiply it by that, and jump, jump, those two cancel. Now, I also need to get rid of the meters. Well, in order for me to get rid of the meters, I need to multiply by meters. So I need to do something like that. And then I know how many centimeters are there in a meter. I know that cancels with this. So I know that this answer turns out to be in KeV. I'll put that over here, KeV per centimeter. Now, the answer, as it turns out to be, and I know some of you don't have Excel or don't feel too comfortable with it, so I'm going to call up calculator here and we will use that instead. So I've got 169,250, and unfortunately I don't have enough room here. Let's see if I can squinch this up a little bit. 169,250, and I'm going to divide that by 1,000 and then divide that result by 100. So what I come up with is well, let's see, I guess I have to annotate this first. So what I come up here is 1.6925 keV per centimeter. So that's the process that you're going to need in order to be able to do your conversions. Now, make sure you've got these right, because if you don't have them right, you're going to be spending a lot of time trying to figure out where you went wrong. So, so there's that. So now let's flip on over here to problem 2. And let's also kind of read it here. So alpha particles with 2.0 MeV have a linear energy transfer in air of 0.175 keV per micrometer. That's supposed to be a mu right there. Didn't really come across there in the document. But what is the specific ionization of these particles in air? Again, the specific ionization, we're going to come from this particular formula. I've got all of that written out here again. I know what the linear energy transfer here is, and I went and spelled that out to micrometer. We know what the average energy is here. All we have to do here is solve this formula for SI, and we come up with this. Yes, I changed the numbers to be something different than what we had here, but the principle still remains the same. So in order for me to be able to generate this particular value, what did I have to do? So let's go here again, and let's see if I can get this to work. So I took 0.4, whoops, 0.4, scrub that out, 0.4 keV per micrometer, which is usually written like that. And we're going to take that and we're going to divide that. And we're going to divide that by 33.85 EV per ionized pair. Now, the problem is that we don't really have the units here as we might need them, say, in the ionized pair per centimeter. What do we have here? Well, we have 0.4 divided by 33.85. If we work that out and we get 0.4 divided by 33.85, I get something here that I can't see. There we go. So I get something along the lines here of, let's see if I can get this activated again. Okay, let's see if it does. Okay. Technology is great when it works. Let's try. Okay, obviously I'm not doing the right thing here. I had it working. It was working so well. just give me the focus. Okay, so I don't know why that was doing that to begin with. So. All right, so I had, I even forgot what the number is now. Let's see. Of course you would. Let's see. 0.012, we'll call it. 0.012. So we end up with 0.012. Now, the problem is that we have a whole mix of units here. We've got KEV divided by EV, and that doesn't directly cancel. And then the ionized pairs, if it's in the denominator of a denominator, then it ends up back on the top of the numerator. And then we have micrometers down here. So this is helping a little bit. This is not. So what I'm going to need to do is I'm going to need to figure out exactly how to get rid of the EV units. I know that 1 KEV is going to be equal to 1,000 EV. And I know that if I do that, that cancels and that cancels. Also, I want to put that into centimeters. How many micrometers are there in a centimeter? Well, micrometers are going to end up being 10 to the minus 6 meters. That's just how they're defined. In other words, if I have 1 meter, I should have, let's see, is it 1,000 or is it 1 million? I believe, let's see, it'll be 10 times 10 times 10 times 10 times 10 times 10. So I should end up with not this, but actually 1 million micrometers. If I'm interested in getting centimeters here, I know there are 100 cm in there. So I should end up, if I just want 1 cm, basically I end up dividing that by 100. And if I want that, if I do something to one side, I have to do it to the other. That means I lose a couple of zeros here. And I end up with, let's see, 1, 2, 3, 4. Should have 4 zeros here. Okay, so now I've got 1 cm is equal to 10,000 micrometers. So in order for me to get rid of the micrometers there, I should have divided by there. So that unit and that unit cancel. So I should end up here. So I need to multiply my result here by, stop the annotation there, multiply it not only by 1,000, but again by 10,000. So I should end up with 118, 168, which is in fact what I end up with. So I should end up with 118, 168 ion pairs per centimeter. So hopefully that makes a little sense here. And I'll just kind of put this away for a little bit. All right, so now let's clear all of this out. Let's see. No, boy, that's kind of permanent there, isn't it? Okay. Let's go on to number 3. Mass attenuation coefficient of copper is 0.0589 squared centimeters per gram for 1.0 MeV photons. The number of 1.0 MeV photons in a narrow beam is reduced to what fraction? by a slab of copper that is 1 cm thick, and it goes ahead and gives you the density of copper. Now, mass attenuation coefficient, that's going to be a different ball of wax here. A mass attenuation coefficient, you might be able to take this particular slide out of the presentation that was given to you, and you can start to see how some of this information starts to fit in with what we're talking about. How does the mass attenuation coefficient relate to the linear attenuation coefficient? And the mass attenuation coefficient, you bring density into the mix. So what does that mean for us? So I went ahead and wrote out a bunch of things here that might hopefully will help you understand all of this. So I've got the mass attenuation coefficient. I'm going to use mu m to represent that. Its units are going to be centimeter squared per gram, and this is the value. Linear attenuation coefficient is going to have units of cm to the -1. At least in this particular example. It could, other examples, it could be different. Density is going to be grams per cubic centimeter. And I believe all of these, the values here are explicitly spelled out for this problem. And then I know it's going to be cutting through. In the problem there, it stated 1 cm of copper. I went ahead and put 2 in there so I could change the problem up a little bit. So the mass attenuation coefficient is going to be the linear attenuation coefficient divided by the density that we saw from this particular slide right here. Now, I can take this formula and rearrange it. If I take the mass attenuation coefficient and multiply it by rho, the density here, then I come up with the linear attenuation coefficient. I'll show you why that's important here in just a minute. So the linear attenuation coefficient is going to end up being the product. It's going to be basically rho, this, times that. So when you multiply that together, again, you can put it in the calculator and you come up with this particular value. Now, what are the units for that particular value? Well, we're taking rho, which is grams per centimeter cubed, and we're multiplying it by centimeters squared per gram. If you do that multiplication there, you can see that the grams are going to cancel out. You've got more centimeters on the bottom than you do on the top, and that leaves you with centimeters raised to the -1 power. That stands to reason. Any sort of unit that you're going to have out of this should end up being a unit of length raised to the -1 power. So we've got that. Now that we have, I told you that story to tell you this one. Now, what are we going to do with that information? Well, if you remember how intensity works exponentially. So that the intensity that you have at some point in as you go through a particular material is going to be equal to the original intensity times E raised to the minus mu times X. This is going to be your linear attenuation coefficient. So what we need to know out of this is what fraction of material is left. Now you might argue, well, we don't know what this particular value is. And as it turns out, we don't have to. What I'm going to do is I'm going to take this particular formula and I'm going to divide it to both sides so that it gets canceled over here. So I'm left with the intensity divided by the original intensity, and that's going to be the fraction of photons that remain. This is also going to be equal to this. Now, I don't know what this is, but once I solve this, because I know this and this, I can figure it out. So this is going to be equal to this times, what is it, 0.52421 times centimeters raised to the -1 power times, in this particular case, I changed the thickness of the copper to 2 cm, and that's a pretty thick copper. So put those values in. If you do all of this, basically you have E raised to whatever the product of this turns out to be. And as it turns out, this becomes 0.350491 if you want to carry it out, or if you want to write it as a percentage, basically you move the decimal point over, you have 35%. And if you go back and you look at this, you have answered the question, it is reduced to what fraction by this slab of copper? It is reduced to a fraction of 35%. Okay, now we're going to move on to problem number 4. Problem number 4 is dealing with the, rather than the mass attenuation coefficient, it is dealing with the atomic attenuation coefficient. Is that more complicated? Yes. Is it located on this same slide here? Yes. So how do we solve this particular problem? Copper has a density that's the same as what you see up here, and a gram atomic mass, or a molar mass, of 63.56. And I'll show you why this is important in a minute. The atomic attenuation coefficient of copper happens to be this for 500 keV photons. Notice how all of these values of the energy keep changing, but we're still using the same principles. What thickness in centimeters of copper is required to attenuate this to half the original number? Okay. So I'm trying to spell out all of these particular values. Of course, I had to change one of them at the very least, and this is the one that I changed. So if I've got an atomic attenuation coefficient of this, the units for this, and it may not be obvious that this is the case, but the units are going to be centimeters squared per atom. Linear attenuation coefficient is pretty much going to be the same. It's a unit of length raised to the -1 power. The density here, that has not changed, gram per centimeters cubed. The Avogadro's number, that's not going to change. There's a number of atoms per gram atomic mass. And then the mass of 1 mole of the element is going to have units of gram divided by gram atomic mass, and it's going to be 63.56. Again, this slide is kind of showing you what's going on here, but it may be a little busy. So what we're doing here is we're finding that the atomic attenuation coefficient, which is what this is equal to the linear attenuation coefficient times the mass of 1 mole of the element divided by the product of the density and Avogadro's number. If you rearrange this particular formula, then the linear attenuation coefficient comes up to be this product on top divided by the molar mass. So when you do all of that, you find out that your linear attenuation coefficient means that you would take, so as I can get my pen working. Okay, all right, great. It's going to give me that. So we're going to take the density, which is 8.9, and that's going to be grams per cm cubed. That is going to be multiplied by Avogadro's number, 6.02, and I'm going to hit through the other two times 10 to the 23rd. That is going to be atoms per gram atomic mass. And that is going to be multiplied by the atomic attenuation coefficient, which in this case is 7.8 times 10 to the -24th cm squared per atom. And all of that mess, which I just drew a line through, ain't it great? It ends up getting divided by the molar mass, which is 63.56, and that's going to be grams per gram atomic mass. Now, please tell me that some of these units end up canceling, and they do. I've got atoms here, cancel with atoms. I've got grams here that will cancel with this. I've got cm cubed and then cm squared. All of those will cancel, and that leaves me here with just cm, and the grams atomic mass actually will cancel. So if you multiply this number by this number by this number and divide it by this, you end up with this value, and all of those units except for this end up canceling. So it's 0.657502 gram cm per cm is what that ends up being. Now, what about the other mess that we've got here? We're trying to figure out exactly what thickness here. Basically, what is X? What thickness of copper makes this value equal to 0.5? Well, again, we start with our equation like this. We take the I naught and put it over here like that. We now know what this particular value is, and we're trying to get to this. Well, how do we get to values that are in the exponent? Aha! If you remember, we can take a natural log. And even if you don't remember, we can take a natural log here of both sides. When we do that, we end up with a mess. But what happens to this over here? We know from our rules that that exponent comes down like that, and it becomes a coefficient, which means that we can start dealing with this a little bit more in ways that we're probably more familiar with. Now, natural log of E ends up becoming 1. Natural log of this, we're looking for whatever the value of X is that makes this 1/2. So we find out that the natural log of 0.5 divided by minus mu is equal to that. So the natural log, and this will end up being a negative number. So the fact that this is negative down here is not really of 0.657502. And when you do that, you come up with this particular value. This is how much copper we're going to end up needing. Why I put this value here, this should actually be cm. Sorry, that's my mistake. So that's how you would work that particular type of problem. Now, number 5, probably the easiest one of the bunch. K and L shell binding energies for cesium are 28 and 5 respectively. What are the kinetic energies of photoelectrons released from these shells as 40 keV photons interact in cesium? What I'm going to do is I'm going to work this particular problem. Of course, I have to have this activated. And I'm going to change this from 40 to 50 keV. Now, if you'll remember, when the photoelectrons, they come into the atom, and they're not straight lines, so they come up, they're doing a little wavy thing, and they come in, and we've got nucleus here, and then we've got these little electrons that are just buzzing around doing their own thing. Okay, so let's say this is a K shell. So we got this thing coming in and gives it just a little bit of energy, releases this, and then you've got a photon that comes out of it. So what's the energy of this guy? Well, this guy coming in had 50 keV. He had to give a little bit here in order for this electron to be released from the shell. As a matter of fact, he had to give it 28 keV. Difference means that the photoelectron here is running off 22 keV. Let's say rather than the K shell, that it interfered in the L shell, and by comparison, it's much cheaper. So it gives it 5 keV to bump it out, which means the photoelectron is running out with 45 keV. So that one's really not too bad. Anyway, I hope this was illuminating for you, and I hope you use it to your advantage. And let me know if you have any questions.